In our last video, we focused on random effects models. Now we're going to talk about mixed effects. Mixed effects are just when we have at least one random factor and at least one fixed factor. So one factor, the random factor, is randomly sampled from the population of levels for that factor, and the fixed factor is all the levels we were interested in. We selected them. You still have issues of random assignment and selection if you have a true experiment versus quasi-experiment, and dependent variable is interval level or greater. We at least have two factors per level. So this is from Lomax and Housevogn's text that we use. I'd like this example. We have a two-factor mixed effects model. We have all four levels of factor A being tested, selected. So this is factor A. We see we have 1, 2, 3, 4 levels of alpha. And then for B, although there's 6 possible levels, we're just going to randomly select amongst them 3 levels, and we end up with 1, 3, and 6. Therefore, A alpha is fixed effects, and B is a random effects model. Here's what that model looks like. We've done this modeling in previous videos and in class. That y sub ij should be y sub ijk, and it is equal to mu plus the effect of alpha, our fixed effects, plus b, our random effects, plus the interaction of those two, plus error. Our hypothesis for the main effect is going to be for fixed factors is the same as fixed factors. It's the difference between means. For the main effect for random effects, it's the same as random effects. It's the variation in means. And for the interactions, a key thing to remember is that they will be an interaction effect between random and fixed is considered random. So we'll use the random hypothesis test. And also, we'll see that that will affect our expected mean squares. Hypothesis for mixed effects, here they are more explicitly. Mu equals, for the null, mu is equal to all other mu's, and for the alternative, there is at least one difference. For the random, again, the variation is equal to 0, whereas the alternative states that it is greater than 0, and the interaction, as I stated before, is, for the alternative, is that there is a variance amongst the means greater than 0. So to be clear, the fixed effect of A is divided by mean squared interaction, whereas the random effects were all divided by the mean square within. So that difference in the F ratio is also in the expected mean squares. When the null hypothesis is true, like it's always been, we just have that residual error term. And in the within term, source of variation, we can see that we still have that error term there, the residual error. So the interaction is treated as a random effect. It is just the residual error plus the interaction. B is treated like a random effect. And if we notice, it just has, in a mixed effects model, error plus its effect, its random effect. Whereas A now has both error and its effect, plus the middle term is going to be the effect of the interaction. So when we talk about dividing these F statistics appropriate, mean squared of interaction is divided by within. For the B term, which is random, the mean squared of B divided by mean squared of within. And for A, because that fixed term has 3 terms, we divide by the interaction term. Assumptions are pretty much the same as before. Little is known, just so you know, about some of the violations. In general, multiple comparisons are not used for random effects models, but we can still look at the fixed effects even across those random effects. In our next video, we're going to start talking about an extension of some of the ideas of random effects, which is a natural extension for us about persons, and we're going to call those the repeated measures models.